I wanted to ask, really quickly with this came up on the quiz, so it's like, the question was rank the following like salts in order to increase in pH based on the solution. So most of them were F's, but then two of them came up like this, where they're both the same category. As in the anion is a conjugate base of weak acid. So is it possible to tell which solution would be more basic without knowing the Ka or Kb?
Never.
Right?
That would be very difficult. I won't be able to do that.
So to be able to tell which one is more basic, the K. Okay, because on the quiz, I didn't know if, you're supposed to know the pump trends or because the K wasn't given. And I didn't know if I had to look at the chart or if you're just supposed to kind of be able to tell different trends. Right.
In this case, I would say you need to look at the chart. Yeah, because of myself, I don't even know. So I think just one.
Yeah.
The case.
Well, when I looked it up, this is a weaker acid.
Weaker acid will make the conjugate base stronger, right?
Yeah, so the solution would be more basic.
Yeah, but normally this actually the answer they won't put. Maybe they will just put you
Yeah,
put it into actually similar.
That's what I did on my first attempt. I ranked them, and then these two that were of the same category, I made them equal, and and when I looked up KB and ranked them accordingly, then it was fine. I just wanted to know, like,
Yeah, just send me that because I won't have, if it's a question, I'm going to ask that from there for. So it can't keep the purpose, If you want to check out a general principle to make some simple judgment, right, that actually should the purpose.
yeah,
And then I guess that if you ask this questions and actually have a more alternative that actually it's not fair that.
yeah.
But those are questions I guess we need to show something like this.
Yeah, well, I think the question that didn't really make it clear if you're supposed to look up Ks or not. If it said, questions the HR, then that would make sense, but.
Yeah, so screenshot it and send it to me so I can check this out, the instructors and
Yeah. This is my first attempt where I set these equal because it's similar, it's incorrect. And then attempt, everything else is the same, except I looked up KAs and it turns out that this was a.
Yeah, I think we need to fix.
Yeah, I can also.
Yeah, same to check. Yeah, same both the one that you got wrong and the one you got wrong. Okay, so if you have the access to this, make sure you do this test. Okay, it is essential for you to do well for the midterm too. It's kind of serve as the test. And we will tell you why is actually the correct answer in the beginning of the lecture. Okay, and then once you've done this, if you have any questions, feel free to actually post the questions through Slido. That is fine too. And just for your reference, okay, there should be actually 4 answers, 4 correct answers for these questions. Okay, do these questions because no matter what, for your midterm 2, you're going to encounter this question. Okay, you need to actually make sure you can do this. This is probably actually one of the most important concepts for the midterm 2. Okay, if you do these things right, you make sure you know this 100%. Okay, so let's get started. Okay, on the board is actually one of the very conceptual questions that you need to actually conquer, so that you can actually do well for your midterm 2. Okay, so we talk about a lot of things, but the main thing for midterm 2 is to calculate a pH of a solution, right? So far, we have been telling you how to calculate pH for a few solutions. The first one is strong acid, strong base, weak acid, weak base, acidic salt, basic salt. Okay, and then the very last one is what? Buffer solution. Okay, so that's all the solution that you're going to encounter. Okay, so let me emphasize again. We have tell you how to calculate pH for the strong acid, strong base, weak acid, weak base, acidic salt, basic salt, and buffer. Okay, 7 different solutions. Okay, so for the strong, let me go to the Hangout so you will see. So in the previous lectures, we summarize all these equations for you, right? So 2 columns basically. Strong acid, very straightforward. Okay. Strong base, that's how you calculate your pH. Okay. Weak acid, weak base is the one that you have the square root of acid concentration times your Kb, or the base concentration, square root of acid concentration times your Ka, or the square root of base concentration times your Kb, right? So this weak acid, weak base, that equation also apply to your acidic salt and then the basic salt, right? So that's actually how you calculate the pH of those 6 different solutions. Okay. The very last solution is buffer, right? And then every time we talk about buffer, there's actually only one equation to use, which is the HH equation, right? So this actually concludes the 7 ways you calculate pH of 7 different solutions. Okay, so everybody fine with this? Okay, so now you know how to calculate pH of different solutions. The most important part for midterm 2 will be Do you know what kind of solution that you have? And that is actually the topic most student fails. Okay, so let's get back to this. Okay, so I list a couple different kind of combinations, right? And ask you what kind of solution that we have. Specifically today, I ask you, okay, can you actually recognize the buffer? Okay. And it turns out most of you actually can actually quickly give me the correct answer, right? And that is the problem that we have. We need to actually resolve that. Okay, so my goal is really let you see what kind of solution that we have. Because if we know what kind of solution we have, we know what equation to use, right? So that is the things you need to actually practice, practice, and practice. Okay, so you need to actually use your homework, using your quiz. Okay, once you read your quiz, once you read a problem, can actually know what kind of solution that you have. Okay, so what is the criteria? Okay, of course, the first thing is actually to know what is strong acid, right? Strong acid, we have only 7 of it, right? So mainly the 7A column, okay? The acidic form of that pretty much give you the strong acid, okay? Strong base, 1A, 2A, oxide or hydroxide, okay? And then weak acid, okay? Every time when you see a molecules, okay, start with H and then go with whatever you have, okay? It's the typical form of weak acid. Weak base, the most common thing one is amine, okay? Do you see I put amine inside this question? Okay, the NH3, right? NH3 is a weak base, okay? Besides that, I also put another thing is NH4Cl, right? So what is that? Salt. Very good. It is a salt, right? How do you know it is a salt? Yeah, Cl is actually always a good clue. Okay, so let me pull out this periodic table so you know what I'm talking about. Okay, so the salt, for a salt, you're going to have Ki ions and Ni ions. Okay, most of the Ni ion will show up for that column. Okay, so if you see something, go with the 7A elements. There's actually a high chance it is a salt. Okay, and then NH4 by itself, NH4 plus. Okay, so let's actually ammonium cation is a weak acid. Okay, and then NH4Cl by itself, it is a acidic salt. Okay, so those are the things that you can actually recognize, so you know what kind of solution you are going to have. Okay, now we want to talk about, so the things we want to talk about today is all about buffer, right? So what is the prerequisite to have a buffer solution? You must have conjugated acid and base. Okay, so let's use this as the example. So just talk about amine NH3 is a weak base, right? And then NH4 plus is its conjugated acid. Okay, so if you have similar amount or comparable amount of conjugated acid and base, then you have a buffer. Okay, once you have a buffer, the way you calculate pH is HH equation. Okay, everybody follow this? Now the key is actually, can you actually identify this? Can you actually identify a solution that contains comparable amount of conjugated acid and base? Okay. So how do we actually prepare this? There are actually multiple ways to generate this. Okay. The first way is you put NH3 for certain concentration and then NH4Cl. Mix them together. This is actually a standard way to prepare a buffer. Okay. So let's say I put one end of this, one end of that. This actually telling you you have a buffer solution. Okay, everybody follow this? Okay. How about, what's the other example I get? Oh, HF. What is HF? Weak acid, okay? You must know HF is a weak acid. Okay, so let's 7 strong acid, you need to actually memorize it. Okay, besides let's 7 HF, you know it should be a weak acid. Okay? So we say in order to have a buffer, you need to have acid and its conjugated base, right? The conjugated base can come in from the basic salt. Okay, because you know this salt, once it dissociates, it's going to give you Na plus and then F minus, right? This is a conjugated acid base pair. Okay, therefore you have a buffer solution. Okay, so this is actually one way. Okay, you have either weak acid and its conjugated basic salt, or you have a weak base with its conjugated acid salt. Okay, so these are the one possibility to prepare the buffer solution. Okay. Any questions for this? No? Okay, yes. Okay, so this, okay, to generate the first line is you have a weak base and then it's weak base and it's conjugated acidic salt. Okay, so this is actually a conjugated acidic salt, right? Typically, you're going to see NH4Cl. Okay, so these are actually the things I input in the Slido, right? So it's very important that you see these things is actually equivalent to, it's going to dissociate and produce this plus that. And this is actually the conjugated acid of the weak base. Yes. Yeah, so buffer is actually a very interesting system. It can only be prepared using weak acid and weak base. Okay. If you want to actually just mix weak acid and weak base together, that's the way you can actually generate the buffer. Okay. So this is one way. The other way, okay, so this is actually one possibility. Okay. Another way to prepare your buffer. Okay, let's start from the weak acid. So HF is actually a weak acid. Okay. Let's say inside here, you have one N HF. Okay, so this is also another option I input inside that multiple choice questions. Okay. So in the first method, what we do is actually we mix weak acid and its corresponding conjugated salt, right? So we have the weak acid and weak base coexist. That's how we get a buffer. Okay, that's one way to get a buffer solution. The second way of preparing the buffer solution is actually you mix a excess amount of weak acid with strong base. Okay, this is another way you prepare the buffer solution. Okay, so why this will actually give you the buffer solution? It's simply because NaOH, once it dissociates, it's going to give you OH minus, right? So this strong acid will do its best, concern itself with any acid existing inside your solution. Okay, so right now you have the weak acid in your solution. You have your strong base. They are going to interact. So it's going to consume the proton here. So you got H2O plus F minus. Okay, and the net result of this interaction is that, let's say you have 1N, 0.5 M in the beginning, right? And then this guy is trying to actually interact with all the acid that it can interact. Okay, therefore, of course, this should multiply the volume so it becomes moles. Okay, so it's going to consume itself fully since it's actually the limiting amount. Okay. And once they do that, the net result once you reach equilibrium is that okay, so the net result is actually you have that much amount of that, this much amount of this. Okay, so once you have the excess weak acid interacting with the strong base, you end up with its conjugated base presenting in a similar amount, right? So right now inside your solution, you have actually a comparable amount of conjugated acid and conjugated base again. And that is actually the criteria for the buffer solution. Okay, so this is actually the second way you generate your buffer. Okay, and then this is actually we're starting from the weak acid, right? You can also start with a weak base, NH3, and then you enter with a strong acid. That's going to give you NH4 plus. Okay, so in this case, you still need to have the excess amount of your weak base. Okay, for example, this actually 1 more, less 0.5 more. Then it's going to minus 0.5, minus 0.5, plus 0.5. In the end, you have 0.5 NH3 and then 0.5 NH4 plus. So you have this and that, which is the conjugated acid and base pair. And they have comparable amount, therefore you also have a buffer solution. Okay, so to recap, there are two ways that you can actually generate the buffer solution. Okay, the first one is you throw in your weak acid and the salt they contain its conjugated base. Okay, so that's actually one way to generate the buffer. Okay, similar concept apply if you have a weak base. Okay, you have this conjugated acid salt. Okay, this is actually how you generate the buffer solution typically. Okay, the other way you do is actually you have a excess amount of weak acid. You add in a strong base. Okay, once they interact, it's going to generate the conjugated base of the weak acid. Okay, therefore you have buffer solution to this interaction. Okay, similarly, you can also start with a weak base in the strong acid. Okay, excess amount of weak base in the strong acid, you can also produce its conjugated acid. Okay, then you still have a buffer solution. So these are the two approaches that you can generate a buffer solution. Okay, any questions for this? So this is actually probably one of the most important things that you have to figure out first. Okay, because if you don't, when you read your questions, you don't know how to do your calculation. Okay, so right now the things that we know for sure is that if we know what solution that I have, I know what equation to use, right? So now the question becomes, okay, can I actually know what kind of solution that I have? Okay, that become the most important things. Okay, that you should actually understand. Okay, so those are the things that, okay, I wish everybody will understand. Okay, it's a very, very important things. Okay. All right, so that's pretty much the purpose of that specific question I posed in the very beginning. Okay, so the answer to that question is, if you look at the first, 1NH3 and 1NH4 plus. Okay, so you should see like the NH4 plus, NH4Cl is actually NH4 plus, right? Which is the conjugate acid of your NH3. Okay, and they are comparable. Therefore, they will give you a buffer solution. So this one is actually correct. Okay. The second one, 1NHF and 0.5M NaOH. HF is a weak acid, right? NaOH is a strong base. Now you have the excess amount of weak acid and small amount of strong base. Therefore, you also have a buffer solution. Okay. Third one, HF and NaF. HF is a weak acid. NaF is the conjugated base soap, right? They give you F minus. So I have a comparable amount of weak acid HF and its conjugated base F minus. Therefore, yes, this one also gives you a buffer solution. The fourth one, 1NHF and 1.1 NaOH. Does this one give you buffer solution? No, it doesn't, right? So what do you have? It's a strong base solution, right? That thing will give you an equivalent of 0.1 N NaOH solution. Okay, because all the weak acid will be consumed, right? So we're going to talk about that in detail today. Okay, so the fourth one is not the correct answer, right? How about the fifth one? 1N NH3. NH3 is a weak base, right? And you have excess amount in 0.5 N strong acid. Yes, this one will give you the buffer. Okay, so the correct answer to this question is actually 1, 2, 3, and 5. Okay, and I hope this is actually something that you can actually understand today. All right, cool. So now we can actually go back to the things we want to actually discuss today. Okay, so on the board is actually the schedule, okay, before your midterm 2. Okay, so we only have 1 week lecture this week, okay, and it will be the spring break and 1 more week for review, and then you have the midterm 2. Okay, so midterm 2 is actually the midterm with a lot of calculations. Okay, midterm 2 is actually the one that really require you to actually do all the calculation quickly and accurately. Okay, so knowing what solution you have is always the step number 1, because once you know what solution you have, you just plug into the equation and you got the answer directly. Okay, so what we're going to do today is actually we're going to try to finish the titration. Okay, and then you're going to learn there are actually 4 different zones of titration, and different zones give you different type of solution. Therefore, you need to actually know what's the associated equation to do the calculation. Okay. And then after the spring break, when you come back, okay, we still have 2 lectures remain. We're going to use 1 to finish chapter 15. Okay, chapter 15 is actually the most simplest chapter in midterm 2. Okay, and there's actually not too much things to cover in chapter 15. Okay, and then we're going to use another lecture to go through questions. Okay, just like the things we did for the midterm 1. All right. Important thing is that on March 8th, Okay, Casa will open to register your midterm to spot. Okay, so make sure you do that before you start to enjoy your spring break. Okay. Well, we are any questions for this? No. Okay. These actually things we want to go through today. So the things we want to go through today is actually tell you what is titration. Okay. Do you guys did the experiment yet? This week? Yeah. Okay, cool. So for the titration, this is actually typical the setup. Okay, typically you have a burette. Okay, inside the burette you have your titrant. Okay, underneath that is actually a flask. Inside the flask you have your analyte. Okay, so for your burette, for the titrant can only be strong base or strong acid. Okay, because you want to know when you actually add in certain amount of acid or base into your solution, it will dissociate 100%. Okay, so for your titrant, it can only be strong base or strong acid. Okay, for your analyte, it can be either strong acid, strong base, weak acid, weak base, buffer solution, whatever. It can be anything. Okay, so what we're going to learn today is that for the titration, basically you're going to have like 4 major different combinations. Okay. Basically, here I list these 4, okay, where the first element is actually your titrant. And then the second element is your analyte. Okay, so with that being said, what this means is for your case number 1 is that you have a strong base as your titrant. You have a strong acid as your analyte. Okay. You can also have a strong base as your titrant, weak acid as your analyte. Okay. And then the 3 and 4 just you swap the acid with base. Okay, so those are the 4 combinations that we can actually go through today. Okay. And these are the 4 steps that we will always use to handle the titration questions. Okay. The first step is to identify your titrant and your analyte. Okay, so the first step is actually identification of your titrant and the analyte. Okay, and then what you need to do is actually you need to write out the ionic equation. Okay, you need to know what is actually your reactants in the ionic form. Okay, and how they are going to react. Okay. The third step is actually to calculate the equivalence point or equivalence volume. Okay, that is actually the volume where the moles of your titrant equals to the mole of your analyte. Okay, and then the way you calculate the mole of your titrant will be the concentration of your titrant times the volume of your titrant, which equals to the concentration of your analyte times the volume of your analyte. Okay, and then the volume of your titrant, we call it as equivalence volume. All right. So once you know your BET, then you will start to define which zones you are at. There are 4 different zones in your titration curve, okay, which we're going to go through later, okay. And depending on where you landed, okay, you need to actually identify what kind of solution that you have. Therefore, you can apply those 7 equations to calculate the pH value. Okay, so this will be the quick summary about what we are going to go through today. Okay, any questions? No? Okay, move on. Okay, so you don't need to actually worry about all these things, okay? You will be uploaded today, okay? So just go to the team, you can see all these things too. So let's talk about this. So this is actually a chart that you have on your Hangout, okay? These two, the strong acid and strong base, highlights your titrate, okay? And then these are your analyte, okay? So SA stands for strong acid, SB strong base, with A, WA is weak acid and weak base, okay? So since acid will only interact with your base, right? So you don't have this, you don't have that, you don't have this, you don't have that, okay? So we're going to start with the simplest case, okay? If your titrant is a strong acid, and then your analyte is a strong base. Oh no, I want to actually go from the easier one, okay? So you can think about things easier. So let's say your titrant is strong base. Your analyte is actually a strong acid. Okay, so let's actually the first situation we want to discuss. Okay. And then one thing that is actually very important in this chapter is actually you should know what it means by the current or the titration curve. Okay, I guess this is actually something to do for your experiment too. Okay, where the y-axis labels the pH value of your solution. Okay. How about x-axis? The volume of your titrant. Okay, so this is actually a very important thing that you should know. Okay, when you do your experiment, this is what you're going to plot. Okay, so I guess you guys are going to use the pH meter and then in all this titrant and see how the pH is going to change, right? Okay, so this is actually what titration curve is. Okay, so let's be clear. This is actually your titrant is a strong base. Let's say your titrant is NaOH. Your analyte, strong acid, let's put HCl as example. Okay. Once you know what your titrant, what your analyte is, okay, then you want to actually plot out the curve for the titration. Okay. So I say there are actually 4 different zones for your titration curve. Okay. Zone number 1 is before you add in any titrant. Okay. So before any titrant, what is the solution that you have? HCl, right? HCl is actually a strong acid, right? So what will be the pH? Low down, right? Okay, so somewhere here, okay, let's actually your zone number 1. Okay. If I say you have 1 NHCl, can you compute the pH? You can do that, right? Because H plus is going to equals to 1, right? So the pH will be negative log of that proton concentration. So log 1 is what? What is log 1? 0, right? Yeah, so the first data point, the pH will be 0. Okay, so let's actually how you do this. Okay, but the key is actually let's actually before titration. So the pH, so solution that you have is just a pure strong acid solution, right? So negative log of proton concentration will give you the pH. Okay. And then what? I start to add in my NaOH, right? So what's going to happen? Okay. Yeah. So here is actually, remember there are actually 4 steps, right? The first step is actually identify your titrant, identify your analyte, right? What's the second step? Write out the ionic equations, right? So what will be the ionic equation here? Your analyte is just H plus, right? I don't write Cl minus because Cl minus doesn't contribute to your pH at all, right? It has to be your weak acid or weak base or proton or OH minus. Those are the ionic species that matters. Okay, so here you know this is actually the ionic species from your analyte, and then you actually add in a strong base, right? OH minus. So the ionic equation is just this: H plus plus OH minus, then give you H2O. Okay. So once you start to add in your titrant, okay, who is going to be concerned? If you add in a lot of this, who is going to be concerned? H plus will be concerned, right? This will be concerned, okay? What does that mean? That means your proton concentration is going to increase or decrease? Decrease, okay? So once your proton concentration decrease, okay? But still, at this stage, okay, you still have excess amount of analyte, right? So what solution do you have? You still have a strong acid solution, right? Just your proton concentration become less. Okay, originally you may have 1 m, right? But after you add in, let's say 0.5 m of strong base, okay, then you end up with 0.5 m of your strong acid. Okay, so you have a lower concentration, but it is still a strong acid solution, right? So there is actually things we call zone 2, right? You still have a strong acid solution. Okay. So once you do that, because the proton concentration got decreased, therefore, when you take the negative log of that, your pH value will gradually increase. Okay. And then it will gradually increase, and at a certain point, you are going to jump up. Okay. And then you're going to hit something called the equivalence point. Okay. And then the volume at that specific point is called the BEP, right? Equivalence point. The volume of the equivalence point. There is actually a point where you have the same amount of titrant and the analyte. Okay. And then this is your zone 3. Okay. At the equivalence point, that is actually your zone 3 because right now you have the same amount of your titrant and analyte. Okay. So in this case, what are we going to have? Okay. It's that the moles of your proton and the mole of your OH minus, they're equal, right? And they will consume each other so that all of them become H2O. Okay, so under the case, inside your solution, all you have is actually H2O, right? What's the pH of H2O? Yeah, so the pH will be 7. Okay, so let's actually the zone 3. Okay, so zone 1, you have strong acid solution. Zone 2, you have strong acid solution. Zone 3, all you have is just water, right? So it's neutral. Okay. So since it's actually water, then the pH will equal to 7. Okay. So beyond the equivalence point is zone 4. Okay. What kind of solution do you have in zone 4? Strong base, right? So how do you calculate the pH here is that you can know how many OH, what is the OH minus concentration beyond equivalence point, right? Take negative log of that, you got your POH, right? And then 14 minus your POH will give you the pH. Okay, so why do we actually talk about this? Because these 4 zones, okay, will give you a different kind of solution when your analyte is not a strong acid. Okay, so let's go through that again. Let's say your titrant is still NaOH. Your analyte is HF. Okay, HF is a weak acid. NaOH is a strong base, right? So if you write out the ionic equation, what you're going to have is HF plus OH minus will give you H2O plus F minus. Okay. So this is the equation into practice. Every time you see a system, right, you want to write out its ionic equation. That's the things that into practice. Okay. And then let's say you have 1N, 100 ml of weak acid. Okay. And then you have 1N OH minus. Okay, and you want to do a titration. Okay. Okay. Again, the y-axis is actually your pH. The x-axis is your volume of your titrant. Okay. So now we want to actually go through these 4 zones again. Okay. Zone number 1 is before titrations, right? So what kind of solution do you have? A weak acid solution, right? So can you actually calculate the pH of that weak acid? So I give you the concentration of my HF, right? I should also provide you the corresponding Ka. Then your proton concentration will equals to the square root of weak acid concentration times your Ka. That's how you get your proton concentration, right? Once you know your proton concentration, take the negative log of that, you got a pH, right? And since it is a weak acid, you can expect the zone 1 should start somewhere below, right? Okay, so let's actually zone 1, right? Zone 2. Okay, I guess we need to actually define the zone 3 first. Okay, let's find out the equivalence point first. When will be the equivalent? What is your equivalence point? The way you calculate the DEP is what? You need to actually compute this, right? The concentration of your acid times the volume of your acid is going to equals to, okay, I guess this is actually your analyte. It's going to equals to a concentration of your titrant times your VEP, right? Here, the concentration of your analyte, in this case, is the concentration of your weak acid, right? Which is 1N. Volume is 100 milliliter, right? So if I put 100 milliliter here, then you finish the things on the left, right? On the right is the concentration of your titrant. In this case, will be also 1, right? And then you want to know how much you should add so that the moles of your titrant is going to equal the mole of your analyte. Okay, so by doing that, you know your VEP will equals to 100 ml as well, right? That means you are going to reach your VEP after you add in 100 ml of your titrant, right? So let's say this is actually 100. Okay. Then that's actually your VEP, right? Okay, now I want to ask you, what kind of solution you are going to have? What kind of solution you're going to have at the equivalence point? So this and that, they have the same amount, right? That means they are going to be consume each other completely. Okay. So once they consume each other completely, what do they generate? H2O and right. So right now, what you have at equivalence point is what? A solution contains a lot of H2O and a lot of F minus. Okay. What kind of solution is that? Basic solution, right? Why is a basic solution? Yeah, so F minus is actually the conjugated base of a weak acid, right? So that conjugated base by itself is basic. Okay, so right now in your solution, what you have is actually a weak base solution, right? So since it's actually a weak base solution, what can you compute? The things you can compute is actually the OH minus concentration, right? So the OH minus concentration will be your F minus concentration multiply the Kb. Okay, so the question is going to provide you the Kb and ask you what's the pH at that point. Okay, so you know you have a weak base, therefore you can compute the OH minus, therefore you can compute your POH, therefore the pH. Okay, so since it is a weak base solution, right? So your pH will be above 7. Any question for this? Because 7 is actually neutral, right? Water has a pH of 7. Right now I have basic solution. So you must have a pH value larger than 7, right? So when you draw this, you know at the VEP, you must have a pH that's actually larger than 7. Okay? So let's actually your zone 3, which you have a weak base solution. Okay. All right, so any question for this? Okay, now we want to actually move to my zone 2. Okay, so right now we know at zone 3, which you have the same mole of titrating and aniline, we end up with a weak base solution, right? How about my zone 2? What kind of solution do I have? So in zone 2, you have excess amount of HF, right? You have limiting amount of OH minus. The OH minus is going to consume some of your weak acid to produce your F minus, right? But you still have a lot of HF inside your solution, right? So you have HF, you have your F minus. What kind of solution is this? We actually practice this for the first 20 minutes, actually. A buffer solution. Okay. Do you see that? Okay, because you have excess amount of HF, right? So once this got fully consumed, you actually convert a good amount of HF to produce your F minus. So inside solutions, I now have HF and then the F minus. They coexist inside your solution. Okay, since you have this conjugated acid and base pair, then you have a buffer solution. Okay, so at zone 2, what you have is a buffer solution. Okay, so since it is a buffer solution, the way you calculate your pH is simply HH equation. Okay. So this is actually a part that got every single student confused. Okay, but if you can see these things clearly, then you probably actually do very well for midterm 2. Okay, yes. Do you know which equation I'm talking about? pH equals to pKa minus log acid over base. Yeah. Okay, so let's actually how you calculate the 3 longs, right? And after that, at the equivalence point, what do you have in excess? The OH minus become the major species inside your solutions, right? Then you have a strong base solution after your equation equivalence point. That means at zone 4, where you have a strong base solution. Okay, since it's actually a strong base solution, all you need to know is actually to compute what is the concentration of those excess OH minus. Therefore, you can compute the pOH, therefore the pH. Okay. So this is the most important part and most confusing part. Okay, let students need to actually figure out. Okay, and I want to figure out this before you go out the door today. Okay, so here I summarize all the calculations that you need to do. Okay, so it looks complicated. Okay, but I want to go through this one together with you. Then you will see it is not complicated. Okay, this is actually the things that we talked about in the very beginning. The titrant and the analyze actually, you have strong base as your titrant, strong acid as your analyte, right? So for example, your titrant is NaOH, your analyze actually HCl. Okay. Zone number 1. What is zone number 1? Zone number 1 is actually the zone that before titration, before you add in any titrant, right? So it's just the solution of your analyte. Since your analyte is a strong acid, right? Therefore, you know the proton concentration was simply equal to the acid concentration provided. Okay. Zone number 2 is actually before your equivalence point, right? Before your BEP. Okay. So in this zone, you have more analyte than your titrant, right? So whatever titrant you add in will be consumed fully. Okay. So all you need to, so you still have a strong acid solution, right? So you need to compute your proton concentration by using this equation. It looks complicated, but it's actually simple and you solve. Okay. In your numerator, you have concentration and the volume. You multiply concentration by the volume for your analyte. Okay, so that's actually the first term. And the second term is actually the mole of your titrant, right? Since they are going to consume each other, the difference between the two is actually the remaining acid inside your flask. Okay, but all you care about is actually concentration, right? So you need to actually divide it by the volume. Right now, the volume will start to change, okay, depending on how much titrant you add into it, right? So the volume here is actually the volume of your analyte plus the volume of your titrant. Okay, since your analyte is actually the weak acid, strong acid, therefore I put HA over there, and then the other thing is actually your base. Okay, but this is actually how you compute. Okay, after a certain amount of strong base, what is the remaining acid concentration? Okay. Zone number 3 is actually at the equivalence point, right? You have the same amount of strong acid and strong base. They are going to consume each other fully. Therefore, all you end up is actually water solution. Since you have water, therefore the pH is simply equal to 7. Okay. And then the 4th stage is actually beyond your equivalence point, right? So in this case, all you have is a strong base solution. Okay, and then you're going to see a very similar equation between the two. The only difference is that right now your base is in excess. Okay, so you put your base in the front, acid in the back. Okay, then you normalize the total volume of your solution to get the OH minus concentration. Okay, so you can see this is changed from the proton into OH minus. Okay, so once you know the OH minus concentration, you can calculate your POH and therefore the pH. Okay, so knowing the zone is critically important because they will actually tell you what kind of solution that you have. Therefore, you can actually compute the pH correctly. Okay, let's go to another one is okay, so here the Tai-Yen is strong base, the analyte is actually weak acid. This is actually a second example we went through. Okay, so zone number 1 is just a weak acid solution, right? Therefore, you compute the proton concentration using the square root of weak acid concentration multiplied by Ka. Okay. Zone number 2, you have a buffer solution, right? So here I write out this proton concentration equal to Ka S over base. Okay, if you take the next block of that give you the pH equals to pKa minus log S over base, which is actually the HH equation. Okay, so here is actually the equation for your buffer. Okay. Third one is actually all your weak acid is concerned by the same amount of strong base. How you generate is actually its conjugated base solution, right? Therefore, you have a weak base solution. Therefore, you compute the OH minus concentration with the weak base concentration multiplied by Kb. Okay. And the very last stage is actually you have excess amount of strong base. Okay, all you calculate is actually what is the remaining OH minus concentration. Again, using the calculate the mole of the base minus the mole of acid divided by the final volume. Okay, so this is actually all the things they need to know for the titration. Okay, this is all. Okay, so you have actually 4 different combinations. Okay, but the strong acid, the first 2 is actually very similar. Okay, you just swap the solution and the titrant. Okay, 3 and 4 is actually very similar. Okay, so when you have a weak acid or weak base as your analyte, the zone 2 will be your buffer solution. Okay, the zone 3 will be its conjugated partner solution. Zone 4 will be the SX titrant solution. Okay, so those are the things that you need to know. Okay, so those are the theory. That's actually all the things you need to know. Okay, any questions? If not, let's go through 2 questions. Okay, for today's lecture. I know it's a lot, but this is actually something you need to actually digest and understand it, because once you understand it, when you read your question again, you feel like everything is actually different. Okay, let's look at this. Calculate the pH of 0.99 gram of some ionic salt. Okay, is added into a 32 ml of 0.5 m benzoic acid. Okay, and then it give you the Ka of that benzoic acid. Okay, you want to know what is the pH of this solution. Okay, what are the keyword here? So when you read through this, right, the first question I ask you to ask yourself is that what kind of solution that I have, right? What kind? Right, you want to actually highlight the things that you have, right? What is this solution? They have a certain amount of C6H5CONA and a certain amount of C6H5COOH. Okay, good. Many of you start to see it's a buffer solutions, right? So, but many of you still don't see that. And that's the problem. That's why students did not do well here. Okay, what's this? Okay, don't struggle at the equation. All you need to know is actually is a strong or weak, right? So it's an acid, right? The title tells you it is an acid, a weak acid, right? So I would say, okay, this is actually a weak acid. And then it's C6H5COOH. The other one's this, right? C6H5COONA. When you see Na, you know the Na is going to dissociate, produce Na plus. Okay, all the remaining will have a -1 charge, right? Therefore, this one is equivalent to C6H5COO minus. Okay, once you have this, then you start to look at this too. Are they conjugated as base pair? Okay, is the difference between these two species just a single proton? If it is, then they are conjugated, right? Therefore, you're going to have a conjugated as base coexist inside a solution, right? Therefore, you have a buffer solution. Can you do this by yourself? That's the things I care about. Okay, so if you know this is actually a buffer solution, what do you do? HH equation, right? So you're going to write out pH equals to pKa negative log proton acid concentration over base concentration. You are going to write these things out, right? And then to calculate pH, the information you need is these three terms: Ka, acid concentration, base concentration. Do you have Ka here? Okay, so you have the Ka, right? Do you have the acid concentration here? It tells you directly, right? Yeah, you can calculate it, right? So the concentration of your weak acid, okay, can be computed by moles of your acid over the volume, right? And then the mole is calculated by the weight of this salt. So sorry, acid is actually this. You actually got the acid concentration directly, right? So the acid is 0.5. Your base, the conjugated base concentration of your A minus is the one that didn't give you yet. Okay, but what it gives you is actually the mass and then molecular weight, right? So the moles of your A minus volume of the solution can be computed. Okay, so this can be computed by 0.99 gram divided by 144.1. That's how many mole of your conjugated base, right? The volume is what? Right? And then you need to actually make sure you divide it by 1,000 so you can have molarity, right? So once you do that calculation, you can get a value of 0.2147. Okay. So here you know the Ka, which is 6.5 times 10 to the negative 5. Acid 0.5. Base 0.2147. Okay. So when you do that when you compute that value, you got 4.1871. So pK is negative log of this value, right? Minus this whole term will give you 0.3671. Therefore, you know your pH is going to have a value of 3.82. Okay. So what is the key here? The key is know what solution you have, right? And then here we know it is a buffer solution is because the two species provide there, okay? You know one of them is actually weak acid, the other one is salt, right? If you actually make that salt dissociate, it produces a species that look like your weak acid, but there's actually proton differences between the two. Therefore, you know it has to be a buffer solution. Therefore, you know you need to use HH equation, right? Once you pull out the HH equation, there are only three things you need to actually pay attention to. Ka, acid concentration, base concentration. If you solve those three terms, plug into the equation, you get your pH. Okay, so if you know what solution you have, calculate this type of question is done. Okay, but you can see how easy the student will actually trap in that situation that you don't know what solution that you have. Okay, so knowing your solution is critically important for your midterm 2. Okay, you must make yourself see what solution that you have. That is the key. Okay, any questions for this? We need to use more to. So you're talking about the titration. Do we do a titration here? So that is actually when you have acid base interacting with each other. Okay, and that interaction must involve a strong acid or strong base. Okay, so strong acid and strong base. Once they see, okay, let's start simplify this situation a little bit. Okay, assuming you actually have a strong acid and a weak base. Okay, they will interact. Okay, strong acid. When we say strong acid, strong base, if they found an interacting partner, they will interact. That is not true for weak acid and weak base. Okay, so when you calculate this change in terms of the mole numbers, it must involve a strong acid or a strong base, which is actually a typical situation you're going to see in the titration. Okay, but for here, there's no such things, right? The species you have in your question is simply a weak acid and its conjugated base. It's retesting. Can you see you have a buffer solution? Okay, yeah, and every time it's buffer, there's only one solution, HH equation, buffer, HH equation, okay? No second way to solve the problem, okay? Okay, the second question. A buffer consists of 0.49 N of this is A, 0.42 N, this is B. Given that the K value for the H2 CO3 are Ka1 equals 4.5 times 10 to the negative 7, Ka2 4.7 times 10 to the negative 11. Calculate the pH of this buffer. What are the keyword here? Buffer, right? So how do we solve this? See, it's so easy, right? HH equation. So pH equals to pKa negative log acid concentration over base concentration. Okay. So now you want to identify three terms, right? Ka, acid, and base. Which Ka should we use? You have Ka1, you have Ka2, right? So it's sort of okay. It's which one should I use, right? That's actually something that we are not very sure at this moment. Okay. So we jump left. Okay, let's look at what is the acid that you have. What is the base that you have? Okay, what's the acid that you have? So one is KHCO3, right? The other one is K2CO3. Okay. What is K? K is 1A element, right? K and the sodium are the most commonly seen stuff that you know. Once you see this, you should actually directly translate this one is HCO3 minus, right? And this one will be what? CO3 2 minus. Okay, so let's say something you need to do. There's something that you need to be very good at. Okay, once you see your sodium, once you see your lithium, once you see your potassium, okay, you know you don't care about that. You care about the remaining part of that formula. Okay, so these are the two things that matters, right? So if you look at these two, are they conjugated as and base? Yes, right. One is actually have one extra proton than the other, right? Therefore, you know this is your acid. This is actually your base, right? So your HA is HCO3 minus. Your A minus is actually CO3 2 minus. Okay. So now, and you know their concentration too, right? Because it says this is 0.49. That is 0.42. And right? So you actually know the concentration. So the second term of your HH equation is actually done, right? Acid concentration 0.49, base concentration 0.42. Now the only thing you want to figure out is actually what's the Ka that I should use, right? So then you look back to here. The Ka that provided is actually what? H2CO3, right? What it means is actually if you start with H2CO3, that you produce one proton, and you got HCO3 minus. That's your Ka1, right? And then HCO3 minus, it can actually further give up another proton. They produce CO3 2 minus. That's your Ka2. Okay. Now, you want to know what is the acid and base species that you have, right? Which is right, and you want to figure out which equation contain these two species. Which one? The first one or the second one? Second one, right? Because this is actually your acid, and that is actually your base, right? So the K2 is actually the equilibrium constant that tie these two together. Okay, therefore, the pKa they need to use is actually use the Ka2. Okay, so here will be equals to negative log Ka2 minus log. Your acid is 0.49. Base is 0.42. Okay. Once you do that calculation, you can get your pH is going to equals to. So if you do the next block, there is 10.3279 minus 0.0669. Therefore, you can get your pH is going to equals to 10.26. Okay. So this is actually a very standard question about the buffer. Okay, so today we're actually mainly talking about a buffer. We haven't actually given you the example about the titration yet, right? Because buffer is actually the one that get students confused the most. So we spend most of time talking about how to calculate the pH of a buffer solution today. Okay. On Thursday, okay, we're going to start to do all the titration questions. Okay, so make sure you will be here because there is a part that students always get confused. Okay, I want to make sure that you will be here. Then we can go through all those questions with you. All right, so that's it for today. Thank you.